All right, let's get into it. Today, we're going to demystify one of the most powerful tools in machine learning for cutting through the noise, principal component analysis, or as you'll usually hear it, PCA. We're going to peel back the layers and see what really makes it tick, step by step.
So, let's kick things off with a problem that, let's be honest, we all face sooner or later. What happens when your dataset has just too much stuff in it? I'm talking hundreds, maybe even thousands of features. The whole thing just becomes a noisy, chaotic mess that's impossible to visualize. You're basically trying to find a needle in a haystack, but the haystack is made of dimensions.
I mean, just take a look at this cloud of data points. Can you really see what's going on here? Is there a pattern, a trend? It's pretty much impossible to tell, right? This is the big challenge with high-dimensional data. All that complexity actually hides the very patterns we're desperately trying to find.
But hold on. What if the data isn't the problem? What if it's just our perspective? What if we could just rotate this whole cloud of points, find a new angle, a new viewpoint that makes that hidden structure pop right out? Well, that right there is the fundamental idea behind PCA.
And here's what that looks like in action. Think of it like this. Imagine you're taking these scattered points and you're casting a shadow of them onto a single line. If you pick just the right line, you can shrink the data from 2 dimensions down to just 1, all while keeping the most important information, the main direction of the spread. It's about simplifying without losing the essence.
Okay, so there's a technical name for this, of course. Dimensionality reduction. The goal is pretty straightforward. You want to reduce the number of features you're dealing with. But, and this is the important part, you do it intelligently, making sure you hang on to the information that really matters the most.
All right, so how do we actually do this? Let's get into the recipe. And you know, like any good recipe, the absolute first and most critical step is all about the prep work. You have to get your data ready.
And that prep work has 2 key parts. First up is mean normalization. All that does is shift your data so that every feature has an average value of 0. Simple enough? Second, what if your features are on totally different scales? You know, like house size in square feet versus the number of bedrooms? One number is going to be way bigger. So you use feature scaling to bring them all into a comparable range. This is super important because it stops one feature from totally dominating the whole analysis just because its numbers are bigger.
Okay, our data is cleaned up and ready to go. Now we can get to the heart of PCA. Let's look at the core algorithm that actually finds those new, simpler dimensions for us.
The process really breaks down into 2 main things. First, we compute something called the covariance matrix, which is just a fancy way of figuring out how all our different features relate to each other. You know, when one feature goes up, does another one tend to go up or down? Then we take that matrix and feed it into this powerhouse of a function called singular value decomposition, or SVD. Seriously, this is where the magic happens.
Now I know what you might be thinking. Covariance Matrix? SVD? If all that sounded like a foreign language, do not worry about it. As the source material points out, you really don't need a PhD in linear algebra to use PCA. At the end of the day, all you need to know is which function to call in your code. The tool is designed to be used, not just understood by mathematicians.
So, the SVD function has done its job, and it's given us our new dimensions, our principal components. But what do we actually do with them? Let's move on to the final step and see how to transform our original data into its shiny, new, lower dimensional form.
So how does this work? Well, SVD spits out this matrix U, which you can think of as a ranked list of all our new axes, from most important to least important. To reduce our data down to, let's say, k dimensions, we literally just grab the first k components from that matrix. This gives us a new, smaller matrix we can call U_reduce. And then you just multiply your original data by this new matrix and boom, you get your final compressed data points.
And there you have it, the whole recipe, summarized right here. Step 1, prep your data. Step 2, calculate the covariance matrix. Step 3, run SVD on that matrix. And step 4, use the result to transform your data. 4 steps, that's it.
So let's just quickly nail down the big takeaways. At its heart, PCA is all about making messy data simple by just finding a better angle to look at it from. And you absolutely have to prep your data first. That part is non-negotiable. The engine room is that powerful combo of the covariance matrix and SVD. And the whole goal is to project your data onto a smaller set of new dimensions that still capture the most important information.
So mastering a technique like this isn't just about math. It's about cutting through the noise to find the real signal. It gives you a whole new way of seeing. So the real question is, now that you can simplify all that complexity, what hidden patterns will you uncover?